Hello everyone, and welcome back to some more remote learning. In today's video, we're going to do some examples on related rates. So remember again that derivatives are rates of change. And as stated in that previous example video, now that we've learned the chain rule and implicit differentiation, we can finally utilize those methods for related rates. So, for example, what if we wanted to know how fast the area of a circle was changing? So how fast an area is changing, that's a rate of change. So if area for a circle is pi r squared, and we want to know how fast that area of the circle is changing, we want to know dA dt, the derivative of our area with respect to time, the rate the area changes with respect to time, how fast that area is changing. And think about it, if we take the derivative of the left-hand side of our equation, that's how we get this dA dt, we also have to take the derivative of our right-hand side of the equation. But nowhere on the right-hand side do we have that variable t, which means that not only is area some function of time, but so is our radius. That's also some function of time. We just don't know what that is. But that's okay, because we can take that rate of change of area and also use the rate of change of our radius to help us find the rate of change we're looking for. So we're going to differentiate the right-hand side just as we would the left-hand side. Pi is just a constant, so constant multiple rule. Leave that out in front, and then we take the derivative of r squared. But similar to taking the derivative of, let's say, y squared with respect to x, y is some function of x, we have to remember that chain rule. Same with r. R is some function of t, we have to remember that chain rule. So the derivative of r squared is not just 2r, but it's 2r times the derivative of the inside, dr dt. So here we have the relationship of the rate of change of area and radius and rate of change of time. So in order to find that rate of change of area, how fast the circle is changing, I would also, in this case, have to know what r is and also have to know dr dt so that I can plug them in and solve for what I want to know. And we're going to do problems like this with some more information down below so that we can solve. But first, let's go through the different steps to solve a related rates problem. First, we're going to list our knowns and unknowns. So like up above, if I was finding the area of the circle, how fast that was changing, my unknown is dA dt, and then hopefully somewhere in my problem, I'll be able to figure out r and dr dt. Either those will be given, or I'll work out those needed variables in step number 4. But we start out by listing our knowns and unknowns, essentially reading through the problem once. And then I want us to read through the problem again. And when we read through the problem a second time, we're going to draw and label a picture for the problem. So if I was talking about how fast the area of a circle was changing, I would draw a circle. Other important information for the circle would be having that radius, because that helps us form the area. And if I knew that radius, that's when I would label it. So we're going to draw and label a picture. Next, step 3, we're going to write out the necessary formulas and derivatives, kind of like I've already done. I wrote out the area formula, and I also took the derivative, because those were the necessary ones that built this relationship of our related rates. I had to know some relationship in order to solve for the unknown variable, and I had to find that appropriate relationship where I can find all my other variables and plug them in. So in the 4th step, we can work out any variables that we need that aren't necessarily given. And then finally, we're going to use all that gathered information, substitute it into our equation, and solve for our unknown. Now I know these steps seem like a lot, but they're kind of intuitive as you go to work through the problem. And if you don't do it in this exact order, it's okay. You could draw and label the picture first. Or you could list all your knowns and unknowns, work out everything you want, and then draw and label the picture to double check that you didn't miss anything. But I will say, even if you think the picture's not necessary, it is important and it's helpful for labeling and bookkeeping all of that information. So let's move down and attempt example 1. So example 1 says that suppose the radius of a circle is increasing at a rate of 2. So that's our given information, and in part A, we're going to find the rate at which the area is changing when the radius is 8 centimeters. So step number 1, I'm going to start with my known and unknowns. What's given and what am I trying to find? So my given information is, from part A, it says my radius is 8 centimeters. So I'm going to say that R equals 8 centimeters. And also from up above, the prompt of example 1, it says that my radius is increasing at a rate of 2 centimeters per second. So if radius is increasing at a rate, centimeters per second, that's the rate of change with respect to time, that's my dr dt. So also that's given is dr dt. And I know that that is 2 centimeters per second. So those are my knowns for the problem. What's my unknown? What am I trying to solve for? I'm trying to solve for the rate at which the area is changing. So because I'm trying to solve for the rate at which the area is changing, that is my dA dt. So I'm going to write solve for dA dt. So I have all my given information. I know what I want to solve for. Let's go ahead and draw and label a picture. So if I have some circle, writing my information down, I know that my radius at a specific point in time that I'm looking for that rate, the area is changing, is when my radius is equal to 8 centimeters. But I also know that this is increasing, let me go ahead and zoom in, at 2 centimeters per second. So not only is my radius equal to 8 centimeters, but I know that it's changing 2 centimeters per second. It is growing, so increasing, a positive. Now for step 3, I'm going to write out the necessary formulas. And if I need to solve for dA dt, well, I need to have area somehow involved in this problem. And an easy formula to start with is that the area of a circle equals pi r squared. I'm trying to solve for dA dt, so I'm going to take the derivative with respect to time. So dA dt, we've already done this up above, so I'm going to just write that dA dt is equal to 2 pi r times dr dt. My pi stayed out in front, and then when I took the derivative of r squared, that became 2r times, remembering that chain rule, dr dt. So if I'm trying to solve for dA dt, are there any other variables that I need in order to solve for it? Well, I ask myself, do I have r? Yep, that was given. All right, do I have dr dt? That was also given. So I have all of my necessary variables to solve for dA dt. So let's just plug those in. So I'm going to get that, I'll do this in a different color since it's our final step, dA dt is going to be equal to 2 pi times my radius of 8 centimeters multiplied by my rate of change, which is 2 centimeters per second, my dr dt. And what does this simplify down to? 2 times 8 is 16, times 2 is 32 times pi, so this is going to be 32 pi and centimeters over seconds, 32 centimeters squared per second. That is how fast my area is increasing. That's the rate of change that my area is increasing with respect to time. 32 pi centimeters squared per second. Now, if you want to enter this into a calculator, multiplying by pi, that 3.14, feel free to. However, I'm going to leave it as 32 pi centimeters squared per second. And there we have it. Our first example related rates problem. Not that bad, as long as we're keeping track of our knowns and unknowns, our givens, and what we're trying to solve for, the rest will fall into place. So let's move on to the next part of this question. Now, when we move on to this next part of the question in part B, the given information from part A does not apply. So I'm starting back up with just what was given to me in the prompt. So when I write out my givens and what I'm solving for, the only given that remains the same is going to be that my radius is increasing at a rate of 2 centimeters per second. So I'm just going to start with this dr dt is 2 centimeters per second right off the bat. Now let's read the rest of our prompt. It says in part B to find the rate at which the area is changing. So again, I'm going to be finding that dA dt when the circumference has a length of 6 pi centimeters. So this is a little different. Now we're talking about circumference. So I'll label circumference in this case as C. So I know that my circumference C is equal to 6 pi centimeters. And what I'm trying to solve for, my unknown, I'm solving for still that dA dt. All right, we've got all our givens and what we're trying to solve for, all our knowns and unknowns at this point in time. Let's go ahead and draw out our picture. So we have a circle where the area is changing. I have some radius. My radius is unknown. That wasn't part of my given information, but I am given that my circumference, so I'll go ahead and draw my circumference in yellow going around the circle. I know that that is my circumference C, that is 6 pi. So if my circumference has a length of 6 pi, and I'm trying to find dA dt, well, dA dt relates to the area, so I need my area formula involved. My area, we know, for a circle is pi r squared, and we've already done this derivative 2 times now, so I'll go ahead and write it out. My rate of change for my area with respect to time is going to be 2 pi r times dr dt. Now let's go ahead and zoom on in. I'm trying to solve for that dA dt, but something's missing. I know my dr dt, that was given to me, but in this problem, unlike up above, I was not given what r is, so I still have to solve for r. And is it possible to solve for r? Yeah, it is, because we're given another piece of information in this problem, that C, our circumference, is equal to 6 pi. And what's the circumference formula for a circle? The circumference C is equal to 2 pi r. So if my circumference is equal to 2 pi r, and I know that C is 6 pi, I can solve for r by dividing by 2 pi. And when I divide by 2 pi, I'll get that my r, my radius, is equal to 3, and that's going to be 3 centimeters. So if I want to, I can go right back over to my section where I have my givens, and I can say, hey, I also now know what r is. My radius r is 3 centimeters. Or even if I don't put that back in with my given variables, I can go ahead and plug everything on in, because now I also know r as well as my original given dr dt. So let's go ahead and solve for that dA dt. So in this case, my change of area is going to be equal to 2 pi times 3 centimeters for my radius times the rate at which my radius is changing is still that 2 centimeters per second. That has not changed. That was part of my original prompt. So I get 2 times 3, which is 6, times 2, which gives me 12. So this is going to be equivalent to 12 pi centimeters squared per second. And that's the rate that my area is changing for part B. Now lastly, for example 1, we're going to find the rate at which the circumference is increasing. So writing down our knowns, or our given information, slash what's known is, well, back from that very beginning. The radius of a circle is increasing at a rate of 2 centimeters per second. So I know my dr dt is a positive 2 centimeters per second. And there's nothing else given for my problem in part C. But what am I trying to solve for? I'm trying to solve for the rate at which the circumference is increasing. So my circumference is what I'm trying to solve for. So solve slash my unknown, however you prefer to label this, is my dc dt, the rate at which that circumference is changing with respect to time. So if I was to draw out my picture, here's my radius r, which I don't know. I do know, though, that it's increasing at a rate of 2 centimeters per second. And I'll make sure to note that it's a positive 2 centimeters per second, so it's getting bigger at 2 centimeters per second, and that's about it. But I can write my circumference formula and take that derivative with respect to time because I'm trying to solve for dc dt. So my circumference c is equal to 2 pi r, which means dc dt, the rate that that circumference is changing, is equal to 2 pi times the derivative of r is just dr dt. Am I able to solve? Yeah, because I know dr dt and there's no other unknowns besides what I'm solving for in my problem. So I'll just plug everything in to get that dc dt. So the rate at which the circumference is increasing, that dc dt, is equal to 2 pi times my 2 centimeters per second, that rate at which the radius is increasing. So dc dt is going to be equal to 4 pi centimeters per second. And notice that this was a different label than up above, because up above I was finding area, circumference is just some length. So it makes sense that I have centimeters as opposed to centimeters squared, and it's the length per time, so centimeters per second. All right, so now that we've worked a lot with the area of a circle, let's move on to a different shape. In example 2, it says that the length of a rectangle is decreasing at a rate of 2 millimeters per second, and that's the length of the rectangle. And the width is also decreasing, but that's at a rate of 3 millimeters per second. So we're going to calculate the following when its length is 8 millimeters and its width is 5 millimeters. So for both of these problems, because I can see that there's no more given information in part A or part B, I'm going to write my given right off to the side, just so that I don't have to redo it for both problems. So in both part A and part B, my given information, or what's known, is a couple different things. I know that the length of my rectangle is 8 millimeters, so I'll say that L is equal to 8 millimeters, and I'll write my L with cursive because otherwise it looks like a 1, and then I'll write that my width, W, is 5 millimeters. And then I also know the rate at which the length and width change. My dl dt is decreasing at a rate, so the length is decreasing at a rate of 2 millimeters per second. So my dl dt, decreasing, meaning negative 2 millimeters per second, and my width is also decreasing at a rate of 3 millimeters per second. So that's going to be my dw dt is a negative 3 millimeters per second. So now let's dive into part A. What am I trying to find? I'm trying to find or solve for the rate at which the area is changing. So in part A, what I want to know, what I'm trying to solve for, slash my unknown, that is going to be dA, the rate at which the area is changing, dA dt. That is what I'm trying to solve for, my dA dt. Let's go ahead and draw a quick picture and then fill in our givens. Since the information is still going to be the same for both, only the unknown is different, I'll go ahead and just draw one picture, but feel free to draw 2 separate pictures. So this is my side L, and I know that that's 8 millimeters. And then I have my width, W, and that's going to be 5 millimeters. I also know dl dt is decreasing at a rate of 2 millimeters per second. So dl dt is decreasing at a rate of 2 millimeters per second. as well as my width is also decreasing at a rate of 3 millimeters per second. Now that I've filled in everything that's been given, I want to find the rate at which the area is changing. So I'm going to need to use the area formula and then take the derivative of that with respect to time. So area for a rectangle equals length times width. So if I'm taking the derivative with respect to time, my left-hand side is going to be dA dt, which is what I'm trying to solve for, but look on my right-hand side, I have two separate variables that are both functions of time. I'm going to need to do the product rule. First times the derivative of the second plus second times the derivative of the first. So first is L times the derivative of my second, that's going to be times dw dt. And then I'm going to add that to my second, which is w, times the derivative of my first, dl dt. And now I'll ask myself, do I have all of my knowns? Do I have enough given information where I can plug it in and solve for dA dt, or do I have any variables that I still need to figure out? I know my length, I know the rate my width changes, I know my width, and I know the rate my length changes. I know everything in order to solve for dA dt. So I'm going to plug all of that right on in. So dA dt is going to be equal to 8 millimeters times dw dt is a negative 3 millimeters per second, plus my w, which is 5 millimeters, times my dl dt, which is a negative 2 millimeters per second. So I have 8 times negative 3, which is going to be negative 24 millimeters squared per second. And then I'm going to be adding that to 5 times negative 2, so really subtracting 10, and that's millimeters squared, and I'll go ahead and zoom in really quick so that's easier to write, millimeters squared per second. So if I have negative 24 minus 10, my change in area with respect to time is a negative 34 millimeters squared per second. 34 millimeters squared per second is the rate at which my area is decreasing. And it's decreasing because it's negative. In part B, I'm going to find the rate at which the perimeter is changing. So I'm going to solve for my unknown, so either solve for or slash, these are my unknowns, and I only have one unknown at the moment, and that is my dp dt. I'll use p to represent perimeter. And I already have my picture off to the side because we've already filled in that given information from our initial prompt. So what we're going to do now is write out the perimeter formula so that we can take the derivative with respect to time. So my perimeter P is equal to, well, think about the perimeter. For the perimeter, we add up all the lengths of the sides. So that's going to be L plus W plus W. So that's going to be 2L plus 2W. 2 times the length plus 2 times the width. Now, I'll go ahead and do dP dt, taking the derivative with respect to time on my left-hand side, and now taking it for my right-hand side, 2 times L, constant multiple rule, pull that 2 out in front. The derivative of L is dL dt, and then I'll add that to 2 times dW dt. I know dL dt because that's part of my given information, and I also know dW dt, so I'll plug those in and solve for dP dt. dP dt is going to be equal to 2 times, what was my dL dt? My dL dt was a negative 2 millimeters per second, so negative 2 millimeters per second, and I'll add that to 2 times, what was my dW dt? That was a negative 3 millimeters per second, so negative 3 millimeters per second. Solving this out, 2 times negative 2 is negative 4, plus 2 times negative 3 is negative 6, -4 plus -6 is going to give me a -10 millimeters per second. That is how fast the perimeter is changing with respect to time. It's decreasing at a rate of 10 millimeters per second. All right, so we've worked with two different figures now, a circle and a rectangle, both two-dimensional figures. We can do related rates not only in 2 dimensions, but in 3 dimensions. So let's go ahead and dive into example 3. Example 3 says that we have a rectangular swimming pool. So essentially we have some rectangular prism. It has a length of 10 feet, a width of 8 feet, and a height of 4 feet. So I'm actually going to start drawing my picture now while I'm reading this information. Again, like I said, those steps that I listed up above, it's just recommended steps that are necessary to complete the problem, but it doesn't mean it has to go in that exact order, just as long as you figure out all the needed information before you solve. So I'll go ahead and draw this pool out. And I'm not the best at 3-dimensional drawing, but we kind of see we have the shape here. The important part is that I label it. So my length L is going to be 10 feet. My width I'll do in a different color. I'll do it in purple if that shows up. That width was 8 feet. And then my height, I'll go ahead and do my height in green. That height is 4 feet. So you can kind of see all of the different aspects of this swimming pool. A length of 10 feet, width of 8 feet, and a height of 4 feet. And then it says if water enters a pool at a rate of 0.25 or a quarter foot cubed per second, how fast is the water level rising? So the other piece of given information that we have is that water is coming into the pool, so it's going in at a rate of 0.25 feet cubed per second. So feet cubed per second, if water is coming in at that rate, that's the amount that the volume is changing. So let's write down all my given information. So I'm given that my length, L, is 10 feet. I'm given that my width is 8 feet. I'm given that my height is 4 feet. And I'm also given my dV dt, the rate my volume is changing with respect to time. dV dt is equal to that 0.25 feet cubed per second. And what are we trying to find? We're trying to find or solve for, or this is our unknown, so however you want to label this, we have to find how fast the water level is rising. That rate that the water level is rising, our dH dt, how fast that water level is rising. Now, we need to figure out some formula to relate our given information in order to be able to find the rate the height is changing. And because we're given the rate the volume is changing, we'll probably go ahead and use that volume formula, the volume of a rectangular prism. So I'm going to say that my volume is equal to, well, its length times width times height. And what I want to know in this case is my dH dt. And I'm going to somehow get dH dt when I go to take the derivative with respect to time. So taking the derivative with respect to time of my left-hand side, that's going to leave me with dV dt, which is helpful because that's something that we know. So we'll be able to plug that in. Now I have to find, well, the derivative of my right-hand side is a product, but it's a product within a product. So in this case, I'm going to have to do the product rule and keep track. So what I'm going to do to make this easier is I'm going to underline my L and W. That's going to be my first, and H is going to be my second. So when I do my product rule, I'm going to take my first function, L times W, times the derivative of my second, that is dH dt, plus my second, which is H, times the derivative of my first. How do I find the derivative of L times W? That in itself is a product rule. So now that I know that I'm finding the derivative of L times W, L will be my first, W will be my second. And if at any point you're confused on this product rule, please refer back to my example video where I do a product within a product towards the end of the product and quotient rules for differentiation worksheet. So go ahead and get some practice if you're confused at any point before moving on. But for now, continuing on, now that I've underlined my next first and second functions, I'm going to have first, which is L, times the derivative of my second, that's my dw dt, plus second, W, times the derivative of L, dl dt. And you'll see here why it was so important to learn implicit differentiation and to really understand that chain rule before we started with related rates, because it's all functions and taking the derivatives of functions. Before I even attempt to simplify, let's ask ourselves if we know enough to solve. Well, I know, what am I trying to solve for? My dH dt. So my dH dt is what I'm trying to solve for. Do I know dv dt? Yes. Do I know L? Yes. Do I know W? Yes. What about each? Yep. I know my L, I know my W. The only two things I don't know are dw dt and dl dt. But think about it. We already know dw dt and dl dt even though it wasn't given information, because what is the rate at which my length of my pool and my width of my pool are changing? If water is coming in and the sides of the pool are always constant, their rate of change is 0. The only thing that's changing is that height. My length and my width are both constant, so when I take the derivatives of constants, that's 0. So both my dl dt and my dw dt are both 0, and this is feet per second. So I'll just go ahead and fill 0 in for those, and now you can see that I have all my variables are known except the one I'm trying to solve for. We can either rewrite this equation and solve for dH dt and then plug in, but I think it's easier just to plug in now, leaving dH dt as that variable. So my volume dv dt, zooming on in a bit, is going to be 0.25 feet cubed per second. So I'm going to write this as 1/4 foot cubed per second. And that's going to be equal to length L of 10 feet times width of 8 feet times leaving dH dt as my variable. That's what I'm trying to solve for, and that's going to get added to, well, let's think about this. If I'm plugging 0 in for dw dt and 0 in for dl dt, that'll be 0 plus 0, because when I multiply 0 by L or W, it goes to 0, and then 0 times H will be 0. So even though I know all of that information, because dw dt and dl dt are 0, it's going to make what I'm adding 0. So plus 0, or I don't even need to include that in my problem. So I have 1/4 foot cubed per second is equal to 10 feet times 8 feet times dH dt. So when I go to solve for dH dt, I'll divide both sides of my equations by 80 feet squared. And when I divide both sides by 80 feet squared, I'm going to get 1/4 divided by 80 is going to be 1/4 times 80, and then feet cubed per second divided by feet squared is going to leave me with feet per second, and that's equal to dH dt. And it makes sense that my height is a length per time for that rate of change, feet per second. So 1/4 times 80, simplifying this down, is 1/320 feet per second. And just to give you some perspective, 1 divided by 320 is 0.003125 feet per second, which is about 0.038, around 0.04 inches per second. So another question I could have asked you is, how fast will it take to fill the pool up? And we could figure that out without even using related rates, just using a little bit of logic. Because the total volume of the pool, if I was to fill it all the way up to the brim, that volume is 10 times 8 times 4 is 320. So if the pool holds 320 cubic feet of water and I'm filling it at a rate of 0.25, it's going to take 320 divided by 0.25. That's how many seconds it's going to take, which is 1,280 seconds or 21.3 repeating minutes, if you want to think about it as that. And this is a good double check because if we know that it's going to take the pool 1,280 seconds to completely fill up, we can take our final answer of 1/320 feet per second, and if we multiply that by the amount of seconds, we should have the total height of the pool. So if it takes the pool 1,280 seconds to fill up, if I multiply that by 1/320, which is the rate at which the height increases, I'm going to get 4 feet. So our answer makes sense and checks out. Let's move on to our next example. And again, this is going to be a 3-dimensional example, except we're switching up the figure. Now we have sand falling out of some chute and onto the top of a conical pile. So we're dealing with a cone. Suppose the height is increasing at a rate of 1 meter per hour and the radius is increasing at a rate of 2 meters per hour. We're going to be calculating the following when the height reaches 10 meters and the diameter is 40 meters. So let's go ahead, write our knowns and unknowns, and draw and label our picture. So doing step 1 and 2 at the same time, I'm going to start by kind of drawing this picture out here. You can see looks like my cone, and I have some chute, and sand is pouring out of the chute onto my cone. If you can envision all this sand falling right on the top of my cone. So the height is increasing at a rate of 1 meter per hour. So h is changing at a rate, so dh dt is increasing at a rate of 1 meter per hour. I also have that the radius is increasing at a rate of 2 meters per hour. So that's going to be my dr dt. And I'm going to calculate the following when the height reaches 10 meters and the diameter is 40 meters. So I know my height is 10 meters and my diameter, which is 2 of my radius, all the way across is going to be 40 meters. So again, I'm going to say that h equals 10 meters and my diameter d is equal to 40 meters. And this is my given information for both parts A and B for examples 4, so I'm not going to redraw this information when I move on to part B, but it's important that it's here. So I'll go ahead and draw a dashed line, now separating my new work from the work that will continue on in part B. But I just wanted to make a note so I don't have to redo this picture. For part A, I'm trying to find the rate at which the volume is changing. So what I'm trying to find or solve for is that dv dt. That's what I'm solving for. So in order to do that, I need to somehow have some volume formula. So I can take the derivative to get dv dt. So my volume for a cone is 1/3 pi r squared h. So when I go to take the derivative of that dv dt, the derivative with respect to time, leaving my 1/3 pi out in front, look, I'm going to have the product rule between r squared and h because those are 2 separate functions of time. So I'm going to underline those so I know that I'm now doing the product rule. And I'm going to put parentheses around all of this because that 1/3 times pi is multiplied to the result of that product rule. So I'm going to have first, which is r squared times the derivative of my second, dh dt, plus second, h times the derivative of my first, the derivative of r squared, is 2r times dr dt. Now, as you can see from my given information, I have pretty much everything in my problem except what is r. I'm going to need some other formula in order to figure out what r is. But what's diameter? Let's go back to this over here. our diameter is 40 and the diameter is 2 times the radius. So if the diameter is equal to 2 times r, and that's all equal to 40 meters, well, dividing both sides by 2, we'll get that r is equal to 20 meters. So now I have everything I need. I have r, I have dh dt, h, and dr dt. All my information I can plug in and solve for that dv dt. So let's go ahead and plug that information in. dv dt is going to equal 1/3 pi times r is 20 meters, so that's 20, and I'm going to leave my labels off for now because I don't have a lot of room left on my problem. However, think about this, the rate at which volume is changing. If I'm dealing with volume and my lengths are in meters, that's going to be meters cubed, and because my rates are all per hour, my dv dt is going to be meters cubed per hour. So I'll make a note of that and I'll drop my labels just for the sake of space. So I'm going to have 1/3 pi times 20 meters squared times dh dt, which dh dt is 1 meter per hour, so that's times 1, plus h of 10 meters times 2 times r, which again is 20 meters, times dr dt, that dr dt was 2 meters per hour. So this is going to be equal to 1/3 pi times 20 squared is going to be 400, and times 1, that's still 400, plus 2 times 2 is 4, 4 times 10 is 40, 40 times 20 is going to be 800. So I have 1/3 pi times 400 plus 800 is 1200, so 1200. And if I take 1200 and divide it by 3, that's going to be 400, and that's all multiplied by pi. And remember, my label is meters cubed per hour. So the rate at which the volume is changing is 400 pi meters cubed per hour. That is how my volume is increasing, and we know it's increasing because it's positive. So my next part, for part B, I'm going to use all the same given information, including the fact that we were able to calculate that radius, because remember, that radius was based on our given information, that diameter, so we didn't do any manipulation from anything that was given in part A, so all of our given information still applies in part B. And we're going to find the rate at which the surface area is changing. So now I'm going to find, and I'll write surface area as S, so I'm finding ds dt. And in order to find ds dt, I need some formula that relates S to my other variables. So I need some surface area formula. And the surface area for a cone is pi r L. So we know r, but what even is L? Because all we have is r and h from our given information above. But L, I'm going to go ahead and draw on my figure that I have. L is the length of the side of my cone, which if you look, we have a right triangle. So we'll be able to figure out L, because if this is h and I have my radius r as the other side of that right triangle, r squared plus h squared equals L squared, the Pythagorean theorem. So scooting this formula over just a bit, so I know that L squared is equal to r squared plus h squared. And I know r squared and I know h squared, so in order to solve for L, I'm going to take the square root of r squared plus h squared. So L is going to be equal to the square root of r is 20, so I'm going to have 20 squared, and that's going to be 20 meters squared, plus h is 10, so that's going to be 10 meters squared, and I'm taking the square root of 20 squared plus 10 squared, which is going to leave me with just meters for my label. But now I need to figure this out. 20 squared is 400, plus 10 squared is 100, 400 plus 100, that's going to be the square root of 500, pulling out that greatest perfect square, that's 100, so this is going to be 10 root 5. And that's 10 root 5 meters for my length. So my surface area again, S is equal to pi r L. So I need to take the derivative with respect to time. So ds dt is going to equal pi times, I got a little bit of product rule here. First, r times the derivative of the second, dl dt, plus second, L times the derivative of the first, dr dt. We still don't have all the information we need. We have r, we have L, we have dr dt, but we don't have dl dt. Is there a way that we can possibly solve for dl dt? Is there some other formula we can relate to get dl dt? Because that's an unknown, but it's not the unknown we're trying to find. So let's see if we can solve for it. Well, if you think about this formula here, L squared equals R squared plus H squared, what if I was to take the derivative of that? Because that would give me a dl dt. Let's go ahead and do it. And I'll do this over here in blue. And I'll go ahead, consolidate some of this information to save myself some room. So I got that L was 10 root 5, and that was 10 root 5 meters. Now I'm going to take the derivative of this formula to see if I'll be able to solve for dl dt in order to use that to eventually solve for ds dt. So taking the derivative of my left-hand side, remembering the chain rule, that's going to be 2L dl dt. And that's going to be equal to 2R dr dt plus 2H dH dt. And I'm running out of room, so I'm going to move everything over. All right, so now that I've moved everything over just a bit, to simplify this problem down, I can divide everything by 2 to get rid of 2. So I just have L times dl dt equals R times dr dt plus H times dH dt. Remember, I already solved for my L. I know my R, dr dt, my H, dH dt, so I'll be able to solve for that still missing rate that I need, dl dt. Once I solve that, I'll now be able to solve for ds dt. So sometimes not everything that you need is given, and you have to do a little bit of work for it, but that's okay. So dl dt is going to equal R, which is 20, times dr dt, which was 2. So 20 times 2 plus H, which was 10, times dH dt, which was 1, so 10 times 1, and that's going to be all over, if I divide both sides by L, my L was 10 root 5. 20 times 2 is 40, plus 10 times 1 is going to be 50. 50 over 10 root 5 is 5 over root 5, or if I didn't want that radical in my denominator, I multiply everything by root 5 over root 5, which leaves me with 5 root 5 over 5, which is just root 5. So dl dt is root 5, that's a length per time. My length is meters, my time is hours. So root 5 meters per hour is my dl dt. So now I have dl dt, I have L, I have R, I have dr dt. I'll be able to solve for ds dt. So my ds dt is going to be equal to pi times R, which was 20, times dl dt, which was that root 5 we just solved for, plus my L, which was 10 root 5, times my dr dt, which my rate of change for my radius was 2 meters per hour, so times 2. That's going to give me, and remember this is the surface area per time, so I'm going to have, if I were to fill in all my labels, meters squared per hour, because I have 20 meters times meters per hour plus meters per hour times 2 meters. That's going to be meters squared per hour added together, which leaves me still with a meter squared per hour for my unit. So I have 20 root 5 plus 20 root 5. When I multiply 10 times 2, that gives me 20 root 5. 20 root 5 plus 20 root 5 is going to be 40 root 5. So I'll have 40 root 5 times pi, and that's going to be meters squared per hour. And now, finally, onto the last problem on this worksheet, example 5. In example 5, we have a 10-foot ladder leaning against the side of a building, and it starts slipping away from the wall at a rate of 3 inches per second. So that base starts slipping away from the wall at 3 inches per second. So 10-foot ladder, it's slipping at a rate of 3 inches per second. How fast is the ladder slipping down the wall when the base is 6 feet from the wall? So we're trying to figure out how fast the ladder is slipping down the wall itself when the base is exactly 6 feet from the wall. Now this is a perfect time to draw a picture and label our knowns and what we're trying to solve for. So if I have some ladder and it's leaning against the wall, I know that that length of the ladder is 10 feet. So I'm just going to call this side L. L is equal to 10 feet. Now it's leaning up against some building and it's resting on the ground. You can see that this is going to make a right triangle. And they also tell me that the base of the ladder is going to be 6 feet from the wall, so I'm going to say that B is equal to 6 feet. What we're trying to solve for is how fast this ladder is slipping down the wall. So if I have a base B, I'll label this side as H. I'm trying to find dH dt. What is dH dt? That's my unknown, how fast that ladder is slipping down the wall. But my other known that I can fill in is that it's slipping away from the wall at a rate of 3 inches per second. Everything else in my problem is in terms of feet, so I'm going to write 3 inches per second as feet per second, and we know that 3 inches is a quarter of a foot. So my rate dB dt is growing because that ladder is slipping away from the wall. It's increasing its distance at 1/4 foot per second. So I've written all my given information down. I need to figure out dH dt. How can I relate dH dt to the other variables in my problem? Well, it's a triangle, so a good place to start is going to be that Pythagorean theorem. So b squared plus h squared is going to equal L squared. My base squared times my height squared is going to equal L squared. And what I'm trying to find is dH dt, so let's go ahead and take this derivative now. So I'll have 2b dB dt plus 2h dH dt equals 2L dL dt. And to simplify everything down, I can divide by 2, canceling out that 2 in every part. So I have b dB dt plus h dH dt equals L dL dt. I'm trying to solve for what? My dH dt. I know my b, I know my dB dt, I know my L, but I don't know h, and I don't know dL dt, and dH dt is what I'm trying to solve for. And in order to solve for that, I need to know what h is, and I need to know dL dt. And one of those we already know. Think about that pool problem above, how those sides of the pool weren't changing. Well, the ladder isn't shrinking, that ladder is constant. So if we were trying to figure out the rate the ladder was changing, it's not changing. So I also know that my dL dt is equal to 0 feet per second. So the only part I don't know is what h is. And then once I figure out h, I'll be able to solve for dH dt. But think about it. Just in the formula above, b squared plus h squared equals L squared. We know b, we know L, we can solve for h using that Pythagorean theorem. So I'm going to say that b squared, which is 6 squared, plus h squared, that's one of my unknowns, not the one I'm ultimately solving for in the end, but one I need to figure out in order to solve for that dH dt. So 6 squared plus h squared is equal to 10 squared. So I'm going to have 36 plus h squared equals 100. Subtracting 36 from both sides, I'll get that h squared is equal to 64, and the square root of 64 is 8. So that's 8 feet for my height. So when my base is 6 feet, at that point in time, my height, h, is going to be equal to 8 feet. So now I have enough given information, I have enough knowns to figure out the HDT. So plugging everything in, I'm going to get b of 6 feet times dB dt, which is 1/4 foot per second, is going to be added to h, which is 8 feet, and I'm trying to solve for the HDT, so I'll leave that as is, and that's going to be equal to L, which is 10 feet, times dL dt, that length isn't changing, so times 0 feet per second. Simplifying this, my right-hand side of my equation goes to 0, so I have 0 feet squared per second, and that's going to be equal to 6/4 or 3/2 feet squared per second plus, and I'll leave this as 8 feet times dHdt. I need to solve for dHdt, so I'll subtract 3/2 to the other side, so I'll get that 8 feet times dHdt is equal to a negative 3/2 feet squared per second, and then I divide everything by my 8 feet, and when I divide everything by that 8 feet, I'm going to be left with dHdt is equal to negative 3/2 divided by 8 is going to be a negative 3/16 feet squared per second divided by feet per second. So negative 3/16 feet per second. That's how fast the ladder is slipping down the wall. So about 2¼ inches per second that ladder is slipping. And with that, we wrap up our related rates worksheet. Again, the important steps for related rates are to essentially write down your knowns and your unknowns, what's given to you, and what are you trying to solve for. And when you label your picture, sometimes as you find that relationship, that formula that you need in order to solve for your main unknown, you're going to get a couple other unknowns in there, and you'll use other formulas, other relationships to solve for them in order to solve for the rate or the variable that's asked for at the start. But hopefully with these 5 example problems, you got some good practice in. I recommend going back to the book or using an online resource and doing more examples than just these 5, just to get a little bit more practice. And once you do a few more problems and feel really comfortable with related rates, continue on to the next video. But until then, good luck with your online learning.